Okay, here we are. It's Thursday, so it's time for our lab session. Looking at little Bayesian population PK in this case. So let me go ahead and I guess remind everybody where we were at with the problem we had at hand. Actually, let me step back to just remind you that what we're going to be doing here is working with a population PK data set that's going to come from a combination of, let's see, where am I going here? Oops, push the wrong button. There we go. That's going to come from a combination of our phase 2 trial with some sparse sampling that was just completed, and that's going to get combined with our phase 1 single dose and phase 1 multiple dose data, which in that case was fairly densely sampled data for those. Let's see, we've got, let's see, that's more or less saying the same thing as we saw before. You've already seen the phase 1 single dose data. We've now got our phase 1 multiple dose data, and this is just the reiterating the design elements that you saw earlier this week. And then for our phase 2 design, we've got some sparsely sampled data from 100 patients, and we're only going to look at the treatment arm for our MI2 drug here. Okay, let's see, what other elements should I point out? Well, we do have an LOQ reported here. We're just going to use a common LOQ for all of the studies, but the way I've set it up for you in this case is if you happen to have a situation where perhaps the LOQ might be study specific or something like that, it would be fairly easy to handle that within the framework that that I've set up here. So we've seen the single dose data. Here's our multiple dose data, and again you can see we've got some densely sampled data for the first day where we have our first 2 doses, and then following the last dose, and then troughs in between. And then the phase 2 data is just fairly sparsely samples with anywhere from 3 samples to 6 samples per individual. And then the model that we proposed. And recall that at the end of last session I suggested some simplifications as a starting point, and then we can add the complications. And in particular, I suggested to you that instead of using the model I had here that involves putting a constraint on Ka, start first by just coding it where we take out that constraint. So we'll just simply model log Ka with a we'll put a log normal prior on that, but we're not going to put any constraints other than that it has to be non-negative in here. And then I also suggested as a first pass also eliminate the dependence upon body weight in here. So just go ahead and knock that out and just do it that way. And what you have now is a model that's nearly identical in form to the one that you used for or that we used for that pop PK example I illustrated, or at least it's identical in terms of the covariate dependence. In other words, it doesn't depend on any. In that case, I had used a constraint on Ka, but for now let's do it without, just because it's simpler to code to illustrate it, and then we can add the other elements in afterwards. So that's what we're gonna do here as a first pass, and then we'll add the other complications in. So let's go ahead and get right down to it. Okay, so go into Windows World here. And what I've done here actually is constructed some version that you don't have. And rather than try to type this all from scratch here, I'm actually going to just follow through an example I've already put together. What you've got actually in your own code is you'll see you've got an ME hands-on 3.r and an ME hands-on 3.text in there. I've added a couple that I stuck this bare bones modifier on it just to do sort of a very basic model that's consistent with the simplifications I just mentioned, to show you that first. Also, I guess remind you what the data looks like here. Let's shrink this thing here, and let me go ahead and open. Let's go up here, hands-on 3. Let me open up the data set. See, it's called FXA non-memdata.csv. In other words, it's the data from all 3 studies written in a non-mem style format. Go ahead and open that up. Should have pre-opened that. It'll take a second here for that to open. But you'll see it's a fairly simple non-mem style data set. And actually, we're going to open it in a spreadsheet here, but under the hood, it's actually a comma delimited ASCII data file. Okay, come on, open up. Okay. Okay, it's not that big a file. Okay, there we go. Okay, let's see if I can make this a little bigger here. View. Okay, why didn't it let me do that? Oh, I see. Okay, a little bigger there. Okay, so you can see here we've got sort of the usual things. We've got our ID column in here for our individual identifier. We've got time, DV for our ME2 plasma concentrations here. You can see we've got dots in here in cases where those values are missing. If the values are missing due to being below quantifiable levels, there's an indicator here, which is a 1 if that's true and a 0 otherwise. Then we've got our dosing events here under amount. The rates in this case are all 0. CMT is 1 for dosing events going into the absorption compartment, and 2 for all of our observation events. EVID is going to be 1 for dosing events, 0 for observation events. Then we've got our II and ADDL, and if we wander down, I believe I actually did use that in some of these downstream. Here, let's do this so we can see that. Okay, let's see, I thought I used, yeah, okay, there we go. So for example, you can see in this subject right here, number 76, I've used that. So this would have been the, which study was this? I believe this, yeah, this was our multiple dose phase 1 study here. So you can see here that we've got a dosing interval of 12 and 15 total doses. In other words, 1 plus 14 additional doses represented there. So that's how that was handled here to deal with the multiple dosing events. And then we've got the steady state indicator is 0 in this case for everything. We've got our body weight, age, gender, and I forget which convention I used for that. And we've got doses repeated over here, but now it's got the dose in every row rather than just on the dosing events, and then a study indicator. The ones we're actually going to use here, let's see, we'll be using most of these, except we're not going to use age, gender, I don't think I used the dose column anywhere. If I did, I think it was only for some plotting afterwards, and it's ditto on the study column. And in fact, in our first pass, I'll even drop the weight here, but we'll add that in as we go. So that's our data set. Okay, so let's go down to what our thing looks like here. Let's open up, we're going to open up WinBUGS, but in this case I'm going to use that black box WinBUGS implementation. So this is WinBUGS embedded inside the black box component builder. So I'm going to go ahead and open that. That will contain all the necessary functions we need from BUGSModelLibrary. Let me go ahead and grab my hands-on 3 bare bones version here. Let's see, let me get rid of our wrapping here. Okay, so this would be what we're going to have here initially is code that's going to be close to but not quite identical to the POP-PK example. So you could have started with the POP-PK example and made relatively minor changes to get to what I've got here. So I guess let's go ahead and start. So as usual, everything's embedded inside of the model block. Then we're going to generate our individual specific random effects in here. And if we go and look at our model up here, let me enlarge this a bit. You can see the way I've got this set up is that we've got the log of all of our model parameters here, clearance, Q, V, the V's and Ka, are normally distributed, but it's a multivariate normal. And in particular, we're going to be doing a multivariate normal with a variance matrix here. We'll be treating that as a full block matrix. Although down here you can see for the prior I didn't use a full block in here, but the estimate itself will be a full block variance covariance matrix here. So we have to specify that multivariate normal. And that's what's going on down here. Now the first thing I've got to do is the way I'm going to specify my various parameters in here is I'll go ahead and initially specify them in terms of our familiar names here. So I've got the log of, I put clearance hat, so that represents the log would actually be the mean of the log of clearance, and I guess clearance hat you can think of then as a typical value for clearance. And the same sort of thing as we go down for Q, for V1, for V2, and then finally for Ka in here. So, and I'll assign those all to this, to a vector. Actually, I'm assigning it to rows within a matrix, but I'm going to assign it to the ith row of a matrix that I'm going to call log theta mean. So the ith row of log theta mean will be the parameters for the ith subject or ith patient in this case. So that will be then that will then contain the means of the logs of our various parameters in here, and those are going to serve then as the mean of our multivariate normal distribution. And you can see that again is written here as dm norm in here. And then for the variance component in here, just as with the univariate normal, instead of specifying things in terms of variance like most normal statisticians would, BUGS specifies it in terms of the inverse. So if it's univariate, it's a precision. If it's in the case of the multivariate analog to that would be the inverse of our variance matrix. So, and that's what this is going to be. It's going to be the inverse of our variance matrix, just like the variance matrix. It'll be 5 by 5 in this case for our 5 parameters. And so that's going to show up there, and then we're going to sample from that to generate what I just called here log theta By the way, these names, again, things like theta, log theta, none of those are reserved names. You can name them whatever you're comfortable with. The only reason I go through this exercise of assigning these values that I have on the right-hand side into components of a vector is because I have to specify a vector over here at this point, and there's no equivalent to something like the C function that you have with R. There's no equivalent to that within BUGS, so I just have to actually take these values here and assign them to elements of a vector and pass it through that way. Let's see here. Now you'll notice I've got a few things hidden off to the right. Those are, think of those as the wizard behind the curtain for the moment. We'll talk about those later. For now, I've got them commented out, and we'll add those in a little bit. Okay, so for the moment, that generates then our individual specific values for log clearance, log Q, log V1, and so on in here. At this point here, I go ahead and take the inverse of that. So now I take my log thetas and I generate my theta values. Here I use my favorite convention of using the link function on the left. But if you prefer, you could have said theta I gets exp of log of theta if you're more comfortable with that. Either way works. And then finally, we have to add in the absorption fractions and lag times for each of the compartments in here. So you've got them for the absorption, central, and peripheral compartments. And those are a requirement of the functions inside BUGSModelLibrary. And then finally down here is where we make the call to our BUGSModelLibrary function. And in this case, since we're not insisting on constraining each individual Ka to be greater than lambda 1, or lambda z if you prefer to call it that, I'm using, instead of the 2CPT model, I'm using 2CPT Ka model, which is the one defined in those terms. And again, recall that the arguments to that then have to be time, representing the either observation or dosing events. Then we have amount, which would contain any of our dosing events in there. Rate, if that played a role, which in this case it doesn't, but we still have to enter it. We've got our inter-dose interval here, the event ID, our compartment, ADDL, SS, and theta in here. Okay, now just recall that going from time to SS, those are defined the same as they are for non-mem. They play the same role. They all have to be vectors of the same length in order for this to work. Otherwise, you'll get an error. So those are all. So that's necessary for this to function. And now recall that the way I did this is we have to have specified in the data set a couple other objects here. We have to have something called start and something called end. So start, now first of all, the overall vector time contains all the times for all the subjects, so stacked on top of each other. So we have to have some way of telling BUGS where does the ith individual's data begin and end, and that's the role that start and end play. So for example, start will be, in the data set, will be a vector. The length of that vector is the same as the number of individuals, and in particular the ith element in there, in other words start I, will contain the index in the time vector corresponding to the beginning of the ith individual's observations. Similarly, end I would then be the index of the time vector where the ith individual's data ends. It would be the last observation for that individual. So for each one of these vectors here, we're using this interval here, start I to end I, then to select out the ith individual's data. And we have to do that for each one of those vectors. And then finally, the last argument in the function is always the model parameters that are being presented in this case as a vector. So theta itself, recall again, is going to be a matrix where the columns correspond to the different parameters and the rows correspond to the different individuals, so that theta I, where I have here theta I comma blank, is going to be the vector of parameter values for the ith individual. And what this is going to return is, on any given call, it's going to return a matrix. The matrix is going to have a number of columns equal to the number of compartments in the model, and the number of rows will be the same as the number of rows inside each of these vectors here. So in other words, you'll have a number of rows equal to the number of times for that individual. And again, I index those in the same way using start I to end I. And for the columns, I specify 1 to however many compartments, in this case 3. Here I give this a name. I called it x hat. Now the quantities that it's going to be returning here into this value are going to be, or into this object, are going to be the amounts in each compartment at each event time. In here, so that gets us close to the thing we're going to want that's going to be related to our observations, but isn't quite the same as our observations. And in particular, since we're going to be dealing with plasma concentrations, we're then going to be assuming that the amount in the second compartment divided by the volume of that compartment will then be our predictor of the plasma concentrations. But we haven't done that yet. Okay, but here we've got the amounts. By the way, notice also that where to go here, CMT, the compartment, plays a role similar to non-mem, but a little bit different, in that CMT really only plays a role here for dosing events, because it says which compartment the dose is going into. But in terms of observation events, if you're in non-mem, it's important because that's going to determine how it calculates the value f that it returns. In this case, it's going to be returning the amounts in all of the compartments, regardless of what the value of CMT is. So in a sense, CMT is irrelevant for observation events. Okay, so that takes care of calculating our amounts. Once it finishes that loop, now we go down to our loop over observations in here. And let me go to, first of all, how do we generate the expected values for our plasma concentrations? And I've kind of alluded to that already. I've written it here. I just noticed I did an adjustment for units. I can't even remember what I had in the data set here, if I even told you what the units were, did I? Well, apparently I put them in the, I did label them on the plots at least here. So I guess I'm assuming my doses are in milligrams and my plasma concentrations are in nanograms per milliliter. So if we want things in sort of the usual, in the usual kind of nice things like liters and liters per hour, we'll have to do some unit adjustments. So that's part of what's going on here. But let's ignore that for a second. Here's the key element here. I'm starting out with the amount in compartment 2 at the ith time, and I need to divide that by the volume of distribution for that compartment for that particular subject. Now, first of all, which parameter is that? Well, if we go up and look at what we have, well, we can see that the third, right here, the third parameter is the one that's associated with our central volume of distribution. And so theta 3 then is going to represent the individual specific value of that volume of distribution. So that's what we need to divide by. That's what we've got going on here. So you can see the second index here, 3, then is picking off the central compartment volume of distribution, and then in order to get the correct value for the ice subject, I have to have another column in my data set that I've called subject here, which indicates which individual that is. So that means I've got to have a column in my data set which is a sequence of values going, integer sequence starting at 1 that I'm going to call subject, and so that the ith value of that would be the corresponding subject value for this data point. So that's taken care of there with our nested indexing. So that's our amount in the central compartment divided by the central compartment volume, and finally 1,000 to convert our units from, I guess what would they be? I guess they would be something like milligrams per liter to micrograms per liter, or equivalently nanograms per milliliter. In here, since we're going to use actually hopefully that's what I set up here, let me double check. Yes, I specified a log normal residual variation here, so that's what's going on here. I first of all take the log of c hat to get it in terms of log. That shows up here as our mean inside of a normal distribution to return the log of the concentrations, and so this model is assuming that the data is actually being passed in a log transform format. So let's see, a couple pieces I stepped right on over. Probably the most important one is dealing with values that were missing due to BLQ, or BQL, however I wrote it. And if you recall that when we were looking at the data set, let's see if it's still there. If we look, I have an object here called BLQ. Let's see, for the multiple dose, there probably weren't a lot of them, but for instance, if I go back to the single dose data, you're going to see a lot of places where DV here is missing, and the corresponding value of BLQ is 1. So those would be cases where we have missing data due to the concentrations being below quantifiable levels. So we need to deal with that. And that's what's going on here then with this I modifier here, where I've got I. For a lower bound, I just leave it blank, so the log of concentration in theory could go all the way down to minus infinity, but the upper end is bounded at the log of the limit of quantitation. Log, of course, being because we're working with log transform data here. Let's see, so that was one key. The only other thing I did here is just this little trick here of taking the maximum of our concentration that versus some small number. And what did I use in this case? I used 10 to the minus 6. Actually, I need to double check and make sure 10 to the minus 6 is really small in context here, but I believe it is. And that's just to deal with things like, well, for example, in some of the items here, the doses may have occurred at time 0, at which so the single dose data where I have a dose at time 0, it's actually the program's actually going to call this code for that point, even though we don't have an observation. It's going to attempt to call it. It'll try to get a predicted value, but of course it's going to be a nonsense value at that point, because this would be a 0 and we'd end up with a numerical error. So this is just covering ourselves for those kinds of instances. Let's see what else. Recall for the priors, I had fairly flat normal distributions, or at least I was using normals with with a mean of 0 and a variance of 10 to the 6th for the logs of a number of our parameters here, and you can see those all represented right here. And then here I've gone and converted them to the original form, not log transformed. Let's see. And then let's see, I'll double check I did that right. Let's see, we wanted a, yeah, for sigma I said use uniform 0 to 100. And that's what we've got right here. And then I have to calculate a precision that corresponds to that. That's the statement right there. Then the other element we needed is we need our omega inverse here. And if again we step back up here, you can see I've got that omega inverse is, we're going to use a prior for that, which is a Wishart with the parameters you see here. We have degrees of freedom equal to 5, and this matrix here, which is somewhere in the neighborhood of probably a rational variance matrix, and I multiply that by the degrees of freedom. And that's actually defined in R in the data set, so we'll take a look at that in a minute. So this is going to be that sort of scale parameter there, and then we have our degrees of freedom here. And then I went ahead and take the inverse of that to get our variance matrix, which actually again doesn't play a role in the model itself, but if we want we can do that here and then return it as an object to monitor when we actually run the MCMC simulations. Okay, so that's again the bare bones code. I haven't included any posterior predictions or anything like that. This is sort of the minimal elements that you would need in order to estimate the parameters. Let's take a look at the corresponding R code to this. Okay, I'll just open it all the way up. Okay, most of the main stuff at the beginning is kind of more of the same here. The only slight trick I had to do is, in addition to putting a different name here for the model name, for the example directory, I just put model name here where you see ME2 hands-on 3. I had to explicitly put ME hands-on 3 because the name of the folder is different from the name of the model in this case. But other than that, it's the usual boilerplate I've been giving you. Again, the only actually I should be careful. The other difference here is now I'm using this black box WinBUGS here, which is the black box component builder containing WinBUGS and the BUGS model library. So I've changed the BUGS directory we're using. Most of the rest of that, let's see, I think pretty much everything is just about the same until we start getting about here where I start defining things like again in this case our limited quantitation is the same for all of the studies, so I'm just kind of hard coding that as a single value of 10. Recall that the trick we're going to use for the case where we have something which is missing for reasons other than BLQ, as I specify an upper bound on our censoring region that's very large, and what I called very large in this case was 10 to the 20th in here, so that's defined as the number big. Next thing I do here is read in our data set, which is pretty much already in a format that we need more or less, other than adding a few extraneous things that are bug specific. By the way, this little bit of code right here, if you wanted to do some practice runs that don't take too long, because of the full data set, I don't recall the exact amount of time, but it's fairly lengthy. I think it's on the order of a couple hours to run the full data set. with the number of iterations I have specified here. So if you wanted to do a subset, you could do that. So if you uncommented the appropriate lines in here, you could do a subset of the data. What did I do here? I think I'm grabbing like a half some of the data and so on. So that would be a way of doing a smaller run. But for now, if we want to do the full run, we read in our data set here. We've got the DVs, recall, used periods in there, and in both R and BUGS world, we're going to want to use NAs for missing. So this next step takes care of that by just doing the as numeric step applied to the DV column. See, our number of observations is just going to be the number of rows inside of our data set. Now we needed that subject column in there, which is a set of sequential integers beginning at 1. The trick that I've shown you in some of the passcode for doing that is appropriate if all the individuals' identifiers are unique. You can just use the trick I showed you before, which is just to use as numeric as character, or I'm sorry, no, it was as numeric as factor, and that will generate the appropriate integer sequence. But if for some reason they're not unique, and for example, non-mem allows the practice of using the same ID for different subjects. As long as they're not adjacent to each other in the data set, it will treat them as separate individuals. Well, if you've taken advantage of that, you have to use a little different trick than the simple one I mentioned before, and the code I've got right here, going from here to here, will do that for you. It will work for those cases where some of the IDs might be duplicates. So that takes care of that. I need to generate, recall, the start and end values, and that's what's going on right here. Oh, actually, I see I added one thing. You could actually take this out, since I already calculated a number of observations up here. So to do start here, you can see I use the trick using the not duplicated function in here, and actually what I did here, is that what I wanted to do? I'm just double checking. Yeah, it's okay. Okay. Yeah, that works. Okay, I was trying to, I guess I redefined ID in this particular instance. Okay. Oh, I see what I did. I've forgotten that I had done this, where I stored the original ID value in a new column and then redefined ID in here, so that's fine. I'd forgotten I did that. Okay, let's see. So we've got put all the goodies in here then. So we've got to put in our numbers of observations, numbers of subjects. So those two things determine the limits on the two loops that were inside the BUGS model. I have to specify my start and end I can calculate this way fairly simply. Once I've got start, calculating end is fairly easy, as you can see here. We've got our subject identifier in here. Recall, I'm going to ignore weight for now, so I commented that out. And then you can see we've got all the sort of usual sort of non-memish elements here. Right down to, whoops. Just go down to here for now. So that's kind of all of our sort of non-mem elements, and you can see all I do here is just grab the corresponding column from our data set. So if things are already in a non-mem data set, that process is pretty easy. Now I have to do a little bit something more with our DV, if you like, with our observations, in order to deal appropriately with my log concentrations and my the log LQ values here, so that I get the appropriate things in here. And in particular, if I have a situation where the DVs are let's see, I'm trying to remember why. I remember why I did this. This allows for if you happen to use one of the conventions some people do, which is to use a negative number for missing values. This would deal with that. In addition, it also takes any zero values that we have, such as at time zero, and converting those to NAs, since time zero values are generally assumed to be zero. In a sense, they're really not data. They're assumptions. So I don't treat them as, whoops, just did a clever thing there. So those you don't want to treat as data as part of the likelihood. And then finally, for the rest of the data, we just want to take the log of dv for that, because we're going to log transform them. And then finally, for our LQ here, if recall, we had that column that if it's 1, that's going to be a case where the value is missing due to BLQ, and we want to have log LQ equal the log of the limit of quantitation. But otherwise, I'm just going to set it to big, which basically everything else will be set to big, including anything which happens to be missing for reasons other than BLQ. And those are the only ones where it'll make a difference. And then finally, here's where I set that scale parameter for the prior distribution on the variance matrix. Okay, so that takes care of our data. I need initial estimates on everything here, so here's some, I forget where I even got some of these. I think most of them were just fairly crude estimates in this case. On this, and the one extra trick that may not be obvious is dealing with the initial estimate for our omega inverse, in other words, the inverse of our variance matrix. So there you need to specify some sort of initial estimate for your variance matrix. So I'm thinking of, in this case, I just as a simple estimator, I just used a diagonal matrix where it's diagonal, where the essentially the central tendency is going to be 0.25 for each diagonal element, but then I put some random variation in it to have some different starting points, and to do that I generated those all from log normal distributions. And so that's all that's going on there. That'll give me a sort of an initial estimate for the variance matrix, and then I use the solve function to get the inverse of that matrix. And then sigma, I just used a little uniform going from 0.1 to 2 here. We save specify all the parameters we want to save in here. Again, most of this is boilerplate for the rest of it, except I have to specify however many iterations, however many burn-ins, and so on. And here to the end is really boilerplate that you've seen in the past. There's really nothing substantially different in any of this. Since I was doing the first simple bare bones one, I didn't even include the posterior predictions. I just do the posterior distributions of the parameters. Okay, let's see. So that's actually the sort of the bare, as I say, the bare bones elements in order to run the model in the format shown here where I did the simplifications. Let me take a little break here before I start adding in those complications. Or as I say break, I mean I'll take a break from for a second and see if there's any questions. One question I got is, why is F1 specified as 1? Can't it be estimated? For the particular data set we have here, no, it can't. And in fact, it's unstated here, but what I'm assuming is that I'm really estimating not clearance Q, V1, and V2. I'm actually estimating clearance over F, Q over F, V1 over F, and V2 over F in this instance. And the reason it can't be estimated here is because all of my doses in this are oral doses. If I had some some intravenous doses, then yes, if I had both intravenous and oral, then yes, I would be able to come up with estimates of F1. Okay, well, let me go ahead and throw in some complications. Let's start with bringing in the covariates here. So maybe what I should do, let me close this and reopen it here without the things crossed out. Let's see here. Okay. Okay, let's see, hands on 3. Okay. Okay, so now we're going to go back and do this. Let's start with bringing in our covariates in here. So what I'm going to do then is use one possible convention here, which is to treat the parameters which have units of flow using making the assumption that they are proportional to body weight raised to the 0.75 power. And then for the parameters with units of volume, namely the 2 volumes of distribution, we'll assume that they are proportional to body weight. So we're going to use that convention here and show how that's implemented. Let's go back to our BUGS code here, and actually I've already got that in here if I get rid of the comments here. Okay, so this is the approach I'm using here. So what I've done is simply brought in body weight in here. So the basic notion here is I'm going to take log for instance, on clearance, I've got log of clearance hat, and I'm adding in the value of 0.75 times the log of the body weight divided by 70. Now the extra bit that's going on here is I've got weight, and I'm going to I guess you could, I'm making one of two assumptions here. You can decide, and let's say that I'm going to use the baseline body weight as my covariate. So what I would do is I would take weight that corresponds to the first data item or the first event for subject I, and I can get that by taking the body weight that's in the at index start I. So I'm using that same index that we've been using before to indicate the beginning of that individual's data. So we're going to go ahead and grab the baseline body weight there. So we're going to make that our covariate, divide that by 70, so I'm normalizing by 70, multiply by 75, and take and add that to the log of clearance. And just to remind you that that's actually equivalent to, let me write it just slightly different just so that it's evident to you what I'm doing here. I could have instead written this like this. Except, oops, what did I do here? I want this to be got an addition where I want a multiplication. Okay, so assuming I've gotten all of my parentheses in there in the right place, that would be the what I've just written right here would be the equivalent expression to the one above it. So I've just taken advantage of identities for logs and so on in the previous one. Okay, so in other words, that what we've got there is equivalent to what I've specified in here. Clearance times body weight over 70 raised to the 0.75. So in the end, we have a number for that clearance hat. Clearance hat you can think of then as being the value of, that would be the typical value of clearance for a 70 kilogram individual. This would be one way you could interpret that. Okay, well, let's get rid of the extra line there. And then similarly, you can see down for the volumes where I just want it proportional to body weight. It looks more or less the same, except we don't have that have the 0.75 multiplying the value. It's just log of weight over 70. So that takes care of our covariate, and that basic idea is something you could do. I mean, another complication you can imagine is instead of assuming that the appropriate exponent here is 0.75, I can make that a parameter instead that needs to be estimated. So you can incorporate that kind of flexibility pretty easily inside here. Let's see, anything else about that? No, I think that's pretty much it for the covariates. The other complication, actually I should stop for a second, see if there's any questions about the notion here of incorporating covariates in this fashion. Okay, nothing popping up so far. If I see something, I can always interrupt and deal with that. Let's see. So the other complication that I didn't deal with is the ones implied right here, where I say, in fact, let me enlarge this so I can highlight it. The other one is right here, where notice I had put the prior not on Ka, but I put it on the difference between Ka and lambda 1. So there the assumption here is that I want Ka not just to be non-negative, I want Ka minus lambda 1 to be non-negative, which would be equivalent of saying I want Ka to be greater than lambda 1. So how can we implement that? Well, let's take a look at least the way I did it here. Let's see. One way we can do that is we can take, let's see, I'm debating whether to do this extemporaneously or not, or just show you the full code on this thing. Where are we? We're running short on time pretty soon. I think I'm going to cheat and actually grab the code rather than try and get it straight, get the algebra straight on a first pass. So let me actually grab the original ME hands-on 1.3.txt model code that was in here. Okay. Okay. And let's scroll down to where I deal with that. Okay, that's going on right down here. This segment of code right here. So first of all, we have to actually calculate the corresponding lambda. And actually I misspoke before. I said constraining it to be greater than lambda z, the same as lambda z. No, lambda 1 I'm actually assuming is the largest of the lambdas, and I want Ka to be even larger. At least that's the assumption I'm talking about making here. And that first of all, I need to calculate lambda in terms of the microconstants of our two-compartment model, and that's what this statement is doing. So you can see we've got our lambda. It's going to be equal to the sum of all of our rate constants plus the square root of this term here, where I've got the square of the sum of the rate constants minus 4 times K10 times K21 and the whole mess divided by 2. Okay, so and it turns out that's just the solution to a quadratic equation that comes up when trying to work this out. And to get to the rate constants here, those are all fairly simple functions then of the parameters as we've got it right now in terms of clearances and volumes. So you can see that here where I've just got K10 is just clearance over V1, K12 is or Q over V1, and K21 Q over V2 in here. So that's just calculating those out. So once we've got our lambda in here, so we've got our lambda at that point. Now what I did is I put the prior not on Ka hat, but on what I referred to here as log dKa hat, which is just the name I use for log of Ka minus lambda 1. So I put the prior on that, and then to get the Ka, I take the lambda, and I have to add that to that difference term, and that's all that's going on here. So I take log dKa hat, take the exponential of that to get Ka minus lambda, and then I add the lambda, and that gives me my Ka hat in here. So now the way I've done that then is I've now got something where Ka hat is now being forced to be larger than lambda. And then finally I use that back up on top here when we generate these. The only difference compared to what I did before is if you look at the other one, it said log Ka hat without the parentheses because I had already defined a term, variable called log Ka hat. In this case, I didn't even bother defining a term called log Ka hat. I just take Ka hat and take the log of that to set as the mean. So that takes care of constraining it. So now the constraint, remind you now, I'm only putting the constraint at the level of the population parameters here, not at the level of individual parameters. At the level of individuals, there is no forced ordering of Ka and lambda 1 and lambda 2. It's only at the population level. The reason for doing that is usually to try and enforce some degree of identifiability here, because without doing that, there's some identifiability problems amongst the various parameters here, and to some degree that can remedy that by putting some constraints like that. The only issue, of course, is that constraint valid? Do we actually know enough about Ka to make that assumption? And that, of course, will depend on any specific case you're working with. But this just illustrates how you can implement it. The other differences in the code that I've got here is now I do introduce calculating the individual, or doing simulations of individual specific parameters. So these are no longer sort of the fitted ones. These are now simulating value. Where am I? I'm looking at the wrong thing here. Where did I go? Where is, oh no, I am right, it is right here. Here I'm now doing simulations, so this is like simulating new individuals that happen to have the same covariates as the original individuals. So these are going to be used to generate my population predictions. And then when we scroll down here, in addition to calling x hat like we did before, I call the two-compartment Ka model again and create something I called x hat pred, which again are simulated values for hypothetical new individuals. And then down here, when I deal with the predictions, or here I've got my my usual likelihood with my data here. I've got my individual predictions here, and then I've got my population predictions right here. So I added all those components in here so we can do things like posterior predictive checks and other measures of fit based upon simulated values. Okay, I think that's about as far as I'm going to, well, actually I should show you what they look like, I guess, when we get done. If we do the, let me close this down. If we do the fit using not the bare bones model but the complete one, let me find where solutions go. There they are. Give you some idea what things look like. Okay, here's the history plots. This was for, I believe it was 10,000 iterations where we kept the last 5,000 and thinned those by 10. So we actually end up with 500 samples per chain with the 3 chains. You can see they look pretty good overall. There's a certain amount of wiggly snake stuff going on, and some of them you can see with the Ka hat, but it's not too bad. You know, if you really wanted to get precise estimates on Ka, for example, you should do probably 5 to 10 times more than what I hear would be ideal. But this already gives you I would say, a moderately reliable outcome here. You just, some of the tail quantiles would be somewhat imprecise. So we got that. Yep, I pushed the wrong button, I guess. There we go. Okay, more of the same. Got all our omega bits there. Let's see, is there anything new here? Not particularly. Again, you get all your values here. Of course, I never spend much time on these, but of course you can look at these and already tell a lot about the posterior distribution and the values here. You know, for example, you can look at this and see, well, pretty clear that Ka is somewhere between about 1.8 and 2.2, for example. Through here, okay, I guess it didn't do the Gelman-Rubin-Brooks plot, so we don't get to see those. But here's our individual predictions for some of the patients in the phase 1 study. So you can see those. Let's see, this is the 1.25 milligram dose group in here, so you can see that the things fit pretty well, but then notice that there's a lot of empty space out here in the tail because that's where there were values missing because of being below quantifiable levels, and you can kind of see that because recall that LOQ was at 10, so you can pretty much see that everything's kind of gets cut off there at 10. You know, we go up to 5 milligrams, and now we're starting to see more samples, but still a few BLQs at the tail. And again, the data we do have seems to be described well, and so on. Now we're getting up to 10 milligram. There aren't too many BLQs left, and still a few here and there at 15, but they're pretty much going away. It doesn't look like there's any at the 20 milligram dose level, and the data is pretty clean. Go on up. You can see it for study 2. This is our multiple dose data. So things again are looking pretty good there. I didn't bother drawing all this. If I was to draw this with more observations, there would be saw teeth in between. Here I've just connected the dots across the trough values. And then we get to our sparse sampling. Again, I haven't tried to interpolate what's happening between observations. I'm just connecting the dots between observations, so you don't get to see a realistic looking profiles as a result. Okay, and then you get the population predictions where you'll see the posterior predictions here. Our credible intervals get a bit broader on these then. Not much more to be said about them, I don't think, at the moment. And then I do things like do some plots at the end to check whether or not our the distribution of random effects seems to be consistent with our assumption of our normal distribution, for example. Boy, log clearance might be a little nicer than that, but it's not too awful. Log Q, got a nasty tail on that one too. Yeah, some of those could be prettier. I suspect there's some shrinkage going on in some of this, but I'd have to look at it more closely to see what's going on in the tails, because I know this stuff was actually simulated using the multivariate normal, so in theory it ought to match up reasonably well. And then you've got some residual plots, and I don't think you'll see a whole lot of pathology there. And our residual terms here are clean as a whistle. Okay, so that's as far as we've taken it this week here, and I'm going to go ahead and sign off at this point. Actually, what we're going to do next week is add some complications to this that I'll introduce during our lecture next week to help you deal with some realistic kinds of problems that you would encounter with population PK things, and for which you probably already know how you would approach them with non-mem, but to give you some idea on how to approach some of those difficulties in the BUGS framework. I guess I'll just stop here, see if there's any last questions, and then head off into the sunset. Okay, nothing's popping up so far, so I guess I'll say goodbye for now. Certainly, if I left you puzzled on any of these things, please put a query in the Q&A section on the course website here, and I'll be glad to respond. Look forward to talking to you again on Monday. Bye for now.